Okay, so that we don't miss sort of education time, as it were, before your mocks, because obviously they're coming up a bit quicker than we would normally have them, I am going to actually give you a taught cover lesson. So I'm just going to go through the volumes of revolution, rotating about the x-axis, rotating about the y-axis, like I've done before, but I've just chosen specific examples that assess a range of different integration skills, because I know that you having a lot of practice the other day, and it's just making sure that we are happy with them. Just apologise now if the resolution is not great, and sometimes it will sort of zoom in and out. Hopefully it won't do it too much, but yeah, we might have to deal with that. So the first question, we're going to be rotating at the x-axis, then I've got a selection around the y. So the region R is bounded by the curve of the equation y equals sine of 2x. The x-axis and the lines x equals 0 and x equals pi over 2. Find the volume of the solid formed when region R is rotated 2 pi radians about the x-axis. So when we're rotating at the x-axis, we are rotating y squared about the x-axis. So it's, the volume will be pi multiplied by the integral between a and b of y squared dx. And I can see that it's popping back and forth. Hopefully as I'm writing it won't be. So in this case, the volume of region R is going to be pi multiplied between 0 and pi over 2. So we've got y squared, so that's sine squared 2x with respect to x. Now, we don't ever like it when we're integrating a trig 1 squared. We've got sine squared or cos squared. We do not want to actually integrate sine squared or cos squared. We need to use one of our double angle formulae. And we need a double angle formulae that's going to give us something without a square. So we're not going to use sine of 2x and square it, because we'll get 2 sine squared cos squared of each of 2x, which we don't want. So we need to use a double angle formula with cos that's going to get rid of our sine squared x. We do need to know our double angle formulae. There may be suggestions that the formula booklet for A-level will be bigger. I am not expecting it to be. So you will have to learn these. So the formula we know, and I'm just doing it to the side. Obviously in an exam you don't have to do it in a different colour, but I would advise you doing it to the side, because you're showing it's working that's relevant, but it doesn't follow on from this, and you don't want to show your substitution within this working. So cos of 2x is equal to 1 minus 2 sine squared of x. It's just x, I went to write 2x, but it's not, it's x. So we obviously want sine squared of 2x. So if this was 2x, then this side, the left-hand side, must be 4x. So I'm just going to rearrange it till I get this form. So 2 sine squared of 2x is equal to 1 minus cos of 4x. So just sine squared of 2x is equal to a half of 1 minus cos of 4x. We leave it in factorised form, because when we put it back in here, we're obviously going to want to take out our factor of a half, because if we don't have to integrate additional stuff, then we want to take it out. So the volume is actually equal to a half pi between 0 and pi over 2 of 1 minus cos of 4x, all with respect to x. So now we've got something reasonable that we can integrate. Sorry, that's the noise of my cat flap in the background. I'm just going to push my door open. My cat is being a bit of an idiot with the cat flap at the moment. Sorry, right, carry on. So now we're at a stage where we can actually integrate it. So a half pi, obviously x minus, so it's 1/4 cos, sine of 4x between 0 and pi over 2. So this is one of those questions where it would have been in your, it probably would have been in the reverse chain rule question, because we've got a function inside of another function, which is when we use the chain rule. All of these can be thought of as substitution. However, it's the kind of substitution I'd expect you to do in your head. Now what I'm going to do is I'm going to do it in a different colour to this side. There's a colour that will stand out again, this blue should work. Obviously, technically, cos of 4x, I could let u equal to 4x. So it'd be cos of u du by dx is just equal to 4. So dx is equal to a quarter of du, which is why it ends up being a quarter of the integral of that. So it ends up being a quarter of sine u, which is a quarter of sine 4x. This is how you can do it, but the reason this is in the reverse chain rule is because they are ones they want you to kind of learn. So I would say if you have cos of 4x, cos of 2x, sine of whatever, where this is not just x, just remember it is 1 over the constant or the coefficient times by it and then the integral of the rest. That's why this is in reverse chain rule chapter, because I just want you to kind of learn it off by heart. That's technically what you do. You don't have to do that working though. I would say please try and remember to do this, at least trig off by heart, and I'm going to refer to another one in a similar situation. So now I can start substituting in, so 1/2 pi, so we've got pi over 2 minus a quarter sine, so it'd be 4 pi over 2, which is 2 pi. Take away 0 minus a quarter sine of 0. Now you might remember off the top of the head that sine 0 is 0. You may not, it doesn't really matter. You might also know that sine of 2 pi is 0, but they're the kind of thing that you probably won't think about. So pi over 2, subtract this ends up being 0, this all ends up being 0. So the whole thing is 1/2 pi times 1/2 pi, which is pi squared over 4. It does just say find the volume rather than the exact volume, so you could put this into decimals, but why put it into decimals if you don't need to? You may as well leave it accurate. Your calculator will not give you pi squared, so if you did type this into your calculator, you would get a decimal answer. So it's not, because it doesn't say find the exact value, that's not a problem. If it said the exact value, obviously think sensibly about it. Okay, so all the rest are going to be rotating about the y-axis now. The only reason that's a bigger focus is because sometimes we need to rearrange an equation. Oh, sorry, it's going a bit mad. Right. The diagram shows a curve of the equation y equals 4 ln x minus 1. The finite region R shown in the diagram is bounded by the curve, the x-axis, the y-axis, and the line y equals 4. Region R is rotated by 2 pi radians about the y-axis. Use integration to show that the exact value of the volume of the solid generated is 2 pi root e times by e squared minus 1. Now the reason that I've put that and sort of underlined it is because it's the kind of question where if you don't keep looking back to this, you may not do things in necessarily the right order, and you may not factorise it to the last minute, which makes it then a bit more challenging. Okay, so we know that when we're rotating about the y-axis, it's a function x squared in terms of y. So what we've got here is obviously y equals, we need to make x a subject to the formula, so that's the first thing that we're going to do. So y equals 4 ln x minus 1. Y plus 1 over 4 is equal to ln x. So therefore x is equal to e to the power of y plus 1 over 4. Now I'm not going to keep it there. I'm going to do a bit more, partially because I need to do x squared, but I'll worry about that in a minute, but partially because I want to make everything as simple as possible. This at the moment is not as simple as possible, and part of the reason is because we know that e is a constant. So remembering that e is a constant will help us, because obviously we can take constants out and we want to look for that. So I can split this into e to the power of y over 4 plus a quarter, so I'm separating that. We know from indices rules that we add the power and we multiply the base. So I know that this can be split into e to the power of y over 4 multiplied by e to the power of a quarter. So now I can then find x squared. When I raise a power to another power, I multiply the index. So it's going to be y over 2, because a quarter times by 2 is a half, times by e to the power of a half. Because that's all one thing, it's like saying 2x squared. If you squared that, it would be 4x to the power of 4. So that's why it can stay there, it's no binomial. So now I've got an x squared, I can... Sorry, I've just looked at my screen and there was a thing right in the middle of your screen, so I hope that it's just on my computer and that the mouse scroller thing wasn't right in the centre the whole time. But I'm 11 minutes in, I'm not going to re-record. Hopefully it won't be when I look back. Anyway, now I've got x squared, I can actually integrate. Now what I'm probably just going to do is do this so that I can use the paper. Obviously you would have tons of space, so just do it underneath. So, the volume is equal to pi integrating between 0 and 4, because it's the x-axis, and 4, of x squared, which is e to the power of y over 2 times by e to the power of a half with respect to y. I probably would write this down first and then write this, but obviously I've staged it up there. This is a constant, so I'm going to take it out. So e to the power of a half pi 0 and 4 of e to the power of y over 2 dy. Now in my next step I'm going to do a couple of things at a time. I'm going to look up here just to be like, am I going in the right direction? Well, it says I want root e. E to the power of half is root e. So I'm going to change e to the power of a half to root e. I'm also, just because of this, going to write the pi in front. So pi root e multiplied. Now I'm going to integrate that. E to the power of a half y. Again, this is one where if I wanted to integrate e to the power of a half y, I may say that u is equal to a half y, so u dash is equal to a half, or du by dy is equal to a half, so dy is equal to 2 du. So therefore what I'm actually integrating is 2e to the power of u, which then gives you 2e to the power of u, which is 2e to the power of a half y. So this is another one where this would be under reverse chain rule. That is a substitution question, but it's a substitution question they want you to learn off by heart. So if you're doing e to the power of any linear function, it's 1 over the derivative of the linear function times by e to the power of that. So I know that reverse chain rule was one that you guys had problems with, which is why I'm referring back to it. So e to the power of a half is going to be 1 over a half, which is 2 e to the power of y over 2 between 0 and 4. Also, learning these ones means you don't have to worry about changing boundaries because we're keeping it in terms of y. That is a y, I'm just drawing it very, let's actually make it clear. It's a little bit clearer. Y over 2. So pi times by root e. Now I could take the 2 out here because I know I need to take it out at the end, but actually we don't tend to take a constant out at this stage, so I'm not going to do it because it wouldn't be a natural reaction, but we can see that we need to do it later. So times by 2e, 4 over 2 is 2, subtract 2e to the power of 0. So that is equal to 2 pi root e times by e squared minus e to the power of 0, which is 2 pi root e times by e squared minus 1 as required. So I factor, I've taken the 2 out here because I know I need to take it out here. e squared minus e to the power of 0. E to the power of 0 is 1, so it is there as required. Obviously you can write as required. This is the, theoretically, according to Miss Goddard, the less pretentious way of doing it. Okay, so we've done an example using truth formulae, we've done an example using a slightly more complex rearrangement. So we're now going to go on to a couple of different ones. So the first one we're going to do, I've selected from the exercises rather than from the examples. This is going to be a by parts question. So this is question 1 from exercise 4B, and it's question 1C. So find the exact volume of the solid generated when each curve is rotated through 2 pi radians about the y-axis between the given limits. So this is x equals the root of 5 minus ln y all over y. So that hasn't printed very well because obviously my printer's going, apparently. Between y equals 1 and y equals 5. So obviously the first thing I want to do is x squared. When I square a fraction, I square the numerator and denominator separately. So the square of the numerator is obviously just 5 minus ln y, and then y squared is y squared. Now the way that I approach this is different to solution bank, so you can always look at what the solution bank does. I think personally my way is easier because they do a lot of rearrangement, integrate it, like I think they do by parts twice because of the way they do it, whereas I only need to do by parts once. Or they sort of do they do? I can't remember, but the solution bank does it differently to me. I think my way is simpler. So what I've done here is I've rewritten it as 1 over y squared times by 5 minus ln y. So what I'm going to do is, when I'm doing by parts, because we kind of end up integrating twice, I don't like using the limits until right at the end. So all I'm going to do, and I'm just going to section this off so it's clear, I'm just going to integrate x squared with respect to y first. So all I'm just going to do is integrate without any boundaries 1 over y squared times 5 minus ln y with respect to y. So that's all I'm going to do. I'm going to do my sort of working to the side here. I'm going to do it in a different colour, but you obviously don't need to. If there's a ln, the part with ln in it is always u, because we can differentiate ln. We can't integrate ln simply, we have to use by parts and use this method of doing it. So 5 minus ln y, well 5 integrates to 0, ln y is 1 over y, so minus ln y is negative 1 over y. That means that v dash, or dv, must be equal to 1 over y squared. We know that 1 over y squared is y to the power of minus 2, so v is going to be y to the power of minus 1 over negative 1, which is negative 1 over y. These kind of algebraic manipulations are ones you do need to get used to and be able to manipulate into this form. Obviously if you kept it in that form, that's okay, it just makes your answer, I think, a bit harder. Okay, so by parts formula is given to you, so it's uv minus the integral, actually I should have done it in a different colour, of v u dash. So therefore, the integral of 1 over y squared times by 5 minus ln y with respect to y is equal to uv, so minus 1 over y times by 5 minus ln y, subtract the integral of vu dash, so negative 1 over y times by negative 1 over y, which is positive 1 over y squared. And we can integrate that easily then to be, so 1 over y squared would integrate to minus 1 over y. We're subtracting it, so it's plus 1 over y. So now we've got our integral. Now we can move into actually doing the volume. So the volume is pi between 1 and 5 of x squared. And I'm just going to write x squared because I can't bother to write all that out. So that'll be pi times by minus 1 over y times by 5 minus ln y plus 1 over y between 1 and 5. I could obviously expand all that out, I don't really want to. If I can keep it factorised, it does make it a little bit easier, I think, personally. So that's equal to pi lots of minus 1/5 times by 5 minus ln 5 plus 1 over 5 take away minus 1 over 1 just gives me 1 times by 5 take away ln 1 plus 1 over 1 is just 1. So now I'm going to start expanding bits. Minus 5 times 5 is minus 1. Sorry, minus 1/5 times 5 is minus 1. Minus 1/5 times by minus ln 5 is plus 1/5 of ln 5. Then I've got plus 1/5. So this part here, minus 1 times 5 is minus 1, but we're timesing that by negative 1, so it's plus 5. Ln 1 is 0, so that just disappears. Then I've got plus 1, but I'm taking away plus 1, so that's minus 1. So what I've got is pi 1/5 of ln 5 minus 1 plus 1/5 plus 5 minus 1 gives me plus 16 over 5. If I put it into my calculator, apologies, I'm going to sneeze. Excuse me. Now, I don't like the fact it's got fractions inside. I'm going to factorise it to be 1/5 of pi times by ln 5 plus 16. The only reason we do that is because if we needed to actually type into our calculator, typing in the fraction once is easier. If there was algebra in here, again, using a fraction once is easier. It says the exact volume. Both this and that are going to be appropriate as the exact volume. It's just that that is nicer because we've got more integers than in our answer, basically, which is deemed as a simplest form. Okay, so we're going to do one more. We're going to do a proper substitution question. This is question 7 in exercise 4b. I know it's quite small on the screen. Right, hopefully it's a bit still now. So using the substitution u equals 2 to the power of y, or otherwise, find the exact value. Now what that says is the integral between 0 and 1 of 2 to the power of y over 2 to the power of y plus 1 all squared with respect to y. So that is a separate question. Now it says using u equals 2 to the power of y or otherwise. Generally, if they suggest a substitution, it is going to be the easiest one. So it might say or otherwise. I would say generally refrain from doing the or otherwise. So u is equal to 2 to the power of y. This is an integration, a differentiation you need to remember, which is that if you're differentiating a to the power of x, that goes to a to the power of x multiplied by ln a. So that's one you need to remember. In pure year 2, somewhere in the integration chapter, differentiation chapter, I believe. So du by dy is therefore equal to 2 to the power of y multiplied by ln 2. Obviously we know 2 to the power of y is u, so I'm going to substitute that in a minute. But I want to rearrange it to make dy equals. So I times by dy and divide by this. So du over u ln 2, because 2 to the power of y is u. So dy is equal to du over u ln 2. So now I can start substituting into here. So this is equal to between 0 and 1. I've got u over u plus 1 all squared. Dy is du over u ln 2. Obviously my u's can cancel. I can take out a factor of 1 over ln 2. So this is 1 over ln 2 times by the integral of 1 over u plus 1 all squared with respect to u. Now again, this is one So I've got 1 over u plus 1 all squared, which is the same as u plus 1 to the power of negative 2. This is another one that in your book would be reverse chain rule. And actually I've just realised I'm not going to put those boundaries in, and I'll talk to you in a minute why. So I'm going to say this implies. Yes, this is an example that would be in a reverse chain rule. But if we use substitution, we can show why it works out how it is. So if v was equal to u plus 2, v dash would be equal to 1. So v to the power of minus 2 would become minus v to the power of minus... Sorry, we are integrating. Sorry, I've done the differentiation there. So that would become minus v to the power of minus 1, or minus 1 over v, which is just the same as minus 1 over u plus 1. So it's actually worked out exactly the same as it would if it was a normal function, because because that is no number, that's just 1, so it means you're multiplying the answer by 1, which means it's just the same as if that was a, b, c, x, y, z, whatever. So this is another reverse chain rule one that they would refer to. It basically means learn it because it's an easy one, but this is how you do it via substitution. I'm not going to. Now I've left the boundaries out, which I didn't, accidentally out of habit, because I can just see that my final answer is going to be relatively straightforward. So to just put 2 to the power of y back in, I can then use my original boundaries. So I'm going to do it without the boundaries. 1 over ln 2 times by, so this will become negative 1 over u plus 1. So that's without boundaries, but this implies then that this is 1 over ln 2 times by minus 1 over 2 to the power of y plus 1. So now what I can do is therefore the integral of 2 to the power of y over 2 to the power of y plus 1 all squared with respect to y is going to be equal to 1 over ln 2 lots of minus 1 over 2 to the power of y plus 1 between the boundaries of 1 and 0. So I'm putting in the boundaries of 1 and 0 at the end because they're my y boundaries. I could substitute and change these, but to me it saves one extra step. But I'm not substituting it into where u is, I'm substituting it into where 2 to the power of y is. So this is equal to 1 over ln 2 multiplied by minus 1 over 2 to the power of 1 is 2, add 1 is 3, subtract minus 1 over 2 to the power of 0 is 1, 1 plus 1 is 2. So that is equal to 1 over ln 2 times by 1/6, which is equal to 1 over 6 ln 2. So that is the exact value of that substitution. So then the question says, because we've got part B, the diagram shows part of the curve of the equation x equals the root of 2 to the power of y over 2 to the power of y plus 1. The shaded region R shown in the diagram is bounded by the curve, the y-axis and the lines y equals 0 and 1. The region is rotated through 2 pi radians about the y-axis to form a solid of revolution. Using your answer to part A, find the exact volume of solid of revolution formed. Well, you can see that x equals this. X squared must be equal to this. The fact there's only 2 marks tells you that there's a relationship, and obviously it's part B, so there's a reason. So B, the volume is going to be equal to pi between 0 and 1, so there's a reason why we use part, of 2 to the power of y over 2 to the power of y plus 1 all squared with respect to y. So that means it's equal to pi times by 1 over 6 ln 2, which is equal to pi over 6 ln 2. And that's it. So hopefully you found this a useful revision of not just volumes of revolution, but actually all the different types of integration that you can have. So worked with the exercise, and on Wednesday, obviously remember it's the math challenge, and then periods 3 and 4 we will look at partial, sorry, not partial fractions, I'm doing that. It's because integration of partial fractions is often something I refer to. Not partial fractions, we're doing parametric integration.